So yesterday we were at this point where we were actually discussing the weight space symmetry, right? I was telling you that you can swap the neurons and the weights and you'll get the same cost, which means that at any of those solutions is okay for that matter. Of course, these are all these are just simplistic figures, right? It just allows you to get a hang of what is going on. Nobody knows how the actual landscape is, especially in a high dimensional space. So I think so that's why yesterday, right, what I showed you was something like this, right, which was to show that so this cost, right, that you're looking at along the y-axis versus the unknowns which you're trying to estimate theta, like the weights and the biases, right. So you can have multiple places, right, where you hit the same local minima. Therefore, any of those solutions is equally valid. The reason why we are saying why we wanted to bring this up is because just to know that when you're solving for a cost function, right, so all this is an optimization problem, right, at the end of the day. So when you're doing that, one is not asking for a global minimum or something, okay, because one doesn't even know where that is and how to get there. And till now, right, we have not seen a systematic way of even solving for the loss, right. The loss could be, as I said, right, depending upon the task. It can be a regression problem wherein maybe you have something like a mean square error as a cost. It can be a classification problem, in which case it could be a cross entropy kind of loss. Till now, we have not seen a systematic. The PLA was just a very simple case, right. Now, today, right, we'll try to look at what is called a gradient descent, which is the accepted sort of a vehicle for doing optimization of in such a high dimensional space. It doesn't mean that, right, it's the best out there. Just that, right, it's mathematically also it's computationally wieldy. Otherwise, you can have unwieldy approaches. I don't know how many of you have heard about things like simulated annealing, graduated non-convexity and all. So those are again methods that can guarantee a good solution, but then they would just take too long to try out, okay, and one doesn't even get there. So if you see, right, most of anything that you read, right, will employ a gradient descent, okay, and a gradient descent is the simplest way to understand it, right, is to sort of take an example. Suppose I had a convex surface like this, right. Now, so for example, right, so the idea is that, right, you want to be there, right, that is your kind of optimum solution, right. That means this is the unknown theta, right, for which the cost is, let's say, this is a loss. You don't have a convex loss, like I said, but let's say if you had it, then a gradient descent would be the most ideal thing to use, because then the idea is that wherever you start from, because your initial guess could be anywhere. For example, I randomly initialize my weights and biases, right, and suppose I start from there. Okay, then if you look at the gradient equation, right, the gradient descent, let me write that down. The gradient descent, we will call this GD. So the gradient descent equation will look like this. So n plus 1th iteration, and it's an iterative algorithm. Okay, it doesn't take you directly to the global minimum because you don't have an analytical gradient and all that. So theta n plus 1 is equal to theta n minus, I'll explain it what these things are. Let's say dou L theta, or okay, let's just say dl theta by d theta, theta equal to theta n, and this can all be vectors, okay. In which case you're looking at a kind of a vector form, or simplest take a scalar form, right. And if you see, so this alpha is called the step size, okay, and there are ways to which we will see later again, right. This is going to be a very quick sort of review on on deep learning. So I won't go into the details that we normally go into, right, when we take deep learning as such. But just to suffice to say that the step size is something very important. Right? If you overstep, right, you could land in trouble. If you take too small a step size, right, you could take forever. So right. So the step size is an important thing. It's of course a number. No, alpha is actually larger than 0, greater than 0, and okay. And so the idea is this, right? So for example, if you're here, okay, which means that you have, a negative gradient, right? I mean, suppose I start here on the curve. So right at that point, I have, a negative gradient, and that, I mean, right, a negative gradient. If you see that negative of then minus of that, right, then that gives you a positive value. And what this means is that if I'm here, let's say if this is theta n, then I would actually head towards theta n plus 1, which will actually take me forward like this, right, in this kind of a direction towards the minimum. If on the other hand, let's say if I'm here, if that is my theta n to begin with, then because you have a positive gradient, right, at that point, negative of that, right, will actually mean that if your theta n is here, then your theta n plus 1, you will, right, it will then take you in the right this one direction. So if you come from here, then it'll kind of, right, take you forward towards the minimum. If you are on a positive gradient, negative of that, right, will then kind of, right, try to. So the idea is that you want to eventually get to this place, right. So you can take small steps and get there, right. That's the idea. So theta n plus 1, you will be here. Then again, right, you might then your theta n plus 1. Okay, then this theta n becomes theta n plus 1. Then this n plus 1, it will then become the next n. And then, right, and then you can imagine if you kind of, right, if you do this continuously, this is, right, iterative. So nth iteration, you go on and on and on. The hope is that, right, you will kind of hit that. Now this is okay if you had a convex surface, right, but as I said, okay, our landscape, right, is not something, right, which is going to be as neat as this. But gradient descent was actually typically meant for right, these kind of surfaces. And but then what turned on, right, what has happened is that this is the one that they use for deep networks also. Okay, but those, I mean, they're just happy, right, hitting a local minimum. So what that means is that, see, your actual surface, for example, it could be, let's draw something. Okay, could be something like that. We don't even know. Okay, so if you're lucky, right, you might have started here, right. If you had started here, just that, somebody gave you some initials just by magic, right, you got parameters to start with from there, then you can hope to hit this point, right, through a gradient descent. Because you see, it's always seeking a direction such that the cost will actually go down. Right, it will never allow for an increase in cost. See, for example, right, when we were here, right, it didn't kind of take you that way, because that would have meant the cost would go up. When you were here, it didn't take you that way, because that again would have meant that the cost will go up, right. So it will never. So that's why it's called a greedy strategy, right. Greedy in the sense that it will always seek the basin or seek the lowest point. So in a way that sounds good, right, because then that's what we want. But at the same time, right, it has its pros and cons. I mean, this is on one hand, it's also a good thing, but on the other hand, right, the bad thing is that if I had started here, unfortunately, then there's no way that I can actually escape this. I mean, I'll end up there, and I have to kind of accept that solution, because I don't even know. Sitting there, think of a hill, think of a hill, right, with, let's say, multiple such mounds, and sitting here, I don't see, right, whether the other side is actually, more whatever, right, is it more down or is it more up? I can't see, right, unless I climb, right. So if I climb here, then maybe, right, I can see that, oh, right, there is a lower point there. But then sitting here, and then when you're not allowing me to increase the cost, right, I'll never end up there. So I can never see what's on the other side, right. So and again, so for example, it could also happen from this direction, right, whichever direction, from wherever you are coming, it can happen that you end up in some. So right, that's called a local minima, because the global is actually here. Okay, but then as far as deep learning algorithms are concerned, as far as deep learning network is concerned, as I told you, there is nothing like a single minima or something, right, because you can have as many, right. The lucky part is, what has turned out to be lucky is that any of those looks fine, right, which is arguable, right, in the sense that but then we have to go with empirical evidence, right. Nobody has been able to show that what you've got is the best, or is a global minimum. You can't prove any of that. So when you have a million parameter space, 60 million, for example, AlexNet I think has close to 60 million unknowns. So where in that space, right? How do you even know where you are? But it turns out that that even a local minimum is kind of acceptable, and you're not really worried about it. And this local minima can also come in various forms, something like that. It could also be something like this. We don't even know, right? It could be a combination of all that. Now, right, you might then kind of one wonders that okay, so right, so I think let me first write down the pros and cons, right? Then I'll again come back to this equation. So let me just simply list the pros and cons of gradient descent, right? So what it can do is it can actually guarantee only a local minimum. So for example, if you start from some other point as the initial point, you may end up somewhere else, right? Your weight configuration could completely change. As it follows, a greedy strategy. As it follows, a greedy strategy. Then point number 2 is that the step size has to be carefully chosen. The step size, that is at alpha, okay? The step size, I mean the alpha, each one will call it by some name, we will call it alpha, has to be carefully chosen. Else it can zigzag. What does this zigzag mean? Is this? See, for example, if suppose I go back to this, and what can even happen is something worse can also happen, right? One thing is that, I mean, if you've chosen a big step size, right, you may actually jump from here to there. Then I think, right, you may just be zigzagging there, because you're kind of right. I mean, you have to take a small step size, right? Otherwise, you'll jump over to the other side, then you'll come back to this side, then again jump over. That's what they mean by zigzag. But zigzag does not just mean that. See, for example, if your surface was, let's say, right, what to say, yeah, right. So it was so right. If it was something like that, then what can happen is, right, depending upon the slope, it doesn't have to be symmetric, right? So what can happen is, if you have a certain slope here, right, which is of course a negative slope, therefore, right, you will go there, you will take a step size, but okay, no, yeah, right. So I don't have to draw it exactly like this. Okay, aha. Okay, so I had something like that, right? Okay, now what I could do is, I could actually end up there. Okay, now if the slope here is higher, and because my alpha is still the same, right, I could actually end up being there, and then from there, right, I could end up being there, and then from there, right, I might just go out completely, right? It can happen, no? So the zigzagging, it doesn't mean that you are actually contained within that basin or something. Even that is not guaranteed. So the step size can be such that, right, you keep oscillating, and then beyond a point you just go out, right? So all of that can happen. Okay, so that's why the step size has to be carefully chosen. Okay, and does not by itself differentiate. Yeah, well, okay, that is fine. I think different initial values. So the other thing is, different initial values can lead to a different local minima. Lead to different local minima. Correct. Yeah, because as I said, right, depending upon where you start with, you might end up with a weight configuration that doesn't even match your first one. But as I said, right, it doesn't seem to be a problem, because people are happy with the final. The empirical evidence shows that, right, it is not at all dependent upon how you start. You can have any random initialization and go. Then, as another point, all functions involved should be, yeah, right, this one is important. All terms or all functions involved should be actually differentiable. All functions involved should be differentiable, because you have that dl by d theta, right, differentiable, correct. So in a way, right, there are kind of say pros and cons, like I said, and but it has been found to work. Okay. Now one can ask, right. So one can ask a question that why did we choose that to be? I mean, intuitively, right? When I showed it, it seemed to intuitively make sense that if you had, you should take a negative of the gradient and move. So it's that's why you have that minus alpha, right, dl by d theta. But there's a more formal way to actually understand that why you take a step like that and why that step size is like that. So ideally, right, you can think of it like this, right? Let's say that I have theta n plus 1, I'm at theta n, right? That's the set of parameters I had in the previous iteration. Then I can say I want to do plus alpha delta theta, right? So I want to move by a delta theta amount. Now which way should I go, right? I mean, okay, right? That's what you want to ask, right? To change my say parameters, but I want to change it in a way that it is actually it should be a meaningful way to change my delta theta, right? Because I can't just arbitrarily add something and move on, right? So I have to have a principled way to actually do it. Okay. So what is a principled way? So what is a principled way to choose? Principled way to choose this guy, to choose delta theta. Okay, a gradient descent is actually a principled strategy. Okay, and that I thought we'll just show. Okay. So you can. So let's kind of look at let right u be a unit vector, right, which tells unit vector which tells me the a direction to move, because the magnitude is anyway 1, right, a direction to move. That means, right, what it means is I am at a certain point on that surface, right, and I want to know which way to go. So in a way, right, what you can do is you can examine, right, u transpose the gradient of theta. Now the gradient, right, I am going to write this now as this symbol. Okay, this I think you are all familiar with, right? The top triangle is delta, the inverted triangle is gradient, right? Gradient with respect to theta, right, L theta. So in a sense, right, you are asking if I have a gradient, then which way should my u be, right? And this can be instead, right, post like, right, minimize with respect to u this quantity u transpose gradient theta with respect to L theta, right? And I'm putting this gradient, right? So this is actually a vector now. Right. So for example, right, you can think of it as some function of, let's say, if it is f of x1 comma x2, then you're looking at dou f by dou x1, then dou f by dou x2, right? I mean, it's like whatever, it's probably very huge, right? But I'm just saying, okay. So in a sense, right, you have a number, right, and you want that right number to be a minimum. Now this quantity, right, we know, right, yesterday itself we saw, right. So this quantity is basically nothing but, so I can write this as minimization u with respect to norm u, right. This we have already seen, right, norm gradient of L, and then cos, let's say whatever, right, let's say cos gamma, right, where let's say, right, gamma is the angle that u makes with respect to a gradient of L, right, with respect to the parameter theta, of course. Now we know that this is 1 because we have chosen this one unit vector, and this we know is actually a positive quantity, right, it's a norm, and therefore, right, if you kind of want this to be a minimum, right, then all of that seem to be centered around the third term, which is cos of gamma, where gamma is the angle between u and so this is the angle between u and the gradient, u and delta theta, not delta theta, the gradient vector, right, and we know that, right, the lowest value, right, I mean, because we are doing this one a minimization, so lowest value that, let's say, cos gamma can take is -1, right, which then means that right, gamma should then be 180 degrees, right, which is why if you see, if you saw that equation, right, it had minus alpha dl by, right, d theta. So this negative of the gradient, right, is basically, it's coming from there, right, because it is supposed to go exactly in the opposite direction, right, with respect to the gradient, because gamma is the angle that u makes with respect to the gradient. Then the other thing, right, is not clear is what should be the step size, right? Okay, now it looks like, I mean, okay, so it looks like which way I should go, I know now. But then the other thing is why, let's say, what should be that step size, right? I mean, I know which orientation, which way I should go, but then how much should I go, right? So this delta theta, we still want to see, right, what should that be, okay? And here, of course, here we saw that it is actually, right, dl by d theta, but that also, right, one can kind of show as to why you choose that, okay? Okay, so in order to do that, right, imagine that you have the cost function, right, which is L, right, and L of theta, right. This is our cost. Now imagine that I take a small step, okay, again a small step. That means I take my alpha to be really small, okay, alpha delta theta, right. I move forward by a small amount. So if you do a Taylor series approximation of this, right, what will that be? What will that be? L theta plus alpha delta theta. Is something wrong or is it okay? Something wrong here? Something is wrong. What is wrong? Of course, I have to write other terms, but what is already wrong here? This should be transpose, right? It's a vector, no? The whole thing should be a scalar. This is a scalar valued quantity, right? Delta theta is a vector, right? By delta theta, I don't mean a scalar, okay? It's like, theta 1, theta 2 in whatever, right? So many weights, so many biases, so everything, right? So it's a kind of a vector. I'm not putting it as a vector explicitly, right? Then what will you get after that? The third term? You are doing a Taylor's, huh? Okay, gradient square, how do you write that? So alpha square, alpha is a scalar, so no point, no problem. The alpha square by, let's say, 2 factorial. Then what happens? Then what do you write? Huh? Exactly. Very good. So what do you do? So you have, sorry, delta, not the gradient. Okay. So delta theta transpose. Then I'll just write this as dou square L. Oh, okay. No, I think we are already using gradient square, right? So gradient square theta, L theta, and then delta theta, right? Okay. This is a Hessian. This is the Hessian of, right, L theta. So matrix containing the second order partial derivatives of L theta with respect to theta, right. So Hessian is the matrix of second, anyway, but then, right, this is not important right now. Second order partial derivatives. So again, right, if you go back to that example f of x1 comma x2, it will be like dou square f by dou x1 square, then dou square f by dou x1 dou x2, dou square f by dou x2 dou x1, then dou square f by dou x2 square, right? 2 cross 2 if you think about it. So matrix of second order partial derivatives. Okay. But right now what we will do is we will actually ignore, and then of course then you will have higher order terms and all of that. So right from the second order term, right, we will just ignore it because our alpha is very small, right. I mean, all this Taylor series approximation is good if you, right, around a neighborhood, right, small neighborhood. So this alpha, right, being small, so we'll ignore all these terms, okay, ignore, and simply retain, right, up to a linear term, okay. We will not take quadratic and all. Now if you look at L of theta plus alpha delta theta minus L theta, that will be a change in the cost, right, because L theta is where I'm already, I have a certain value for L at theta and I'm trying to move forward, right, which is my alpha delta theta, and this is nothing but alpha delta theta transpose gradient of L theta. Now what do you want this to be, right? I mean, you want to move in a manner such that the cost should go down, no, right? That means my L theta plus alpha delta theta should be less than L theta, right? That's what I want, no? I want my cost to go down, right? I want to move in a manner such that my cost goes down. That means, right, that means you want this to be a negative sort of a quantity, right, and maybe as small as possible, right? How much can you go? But you want it to be a negative because then you are kind of going down, whichever way, whether you start from there or whether you start from here, you want to move in a direction such that the cost will go down. Of course, if you are doing gradient ascent, then it will be ulta, right? You have gradient descent, you also have gradient ascent, okay. With gradient ascent, then you want the cost to go up. Okay, but in the okay, let's forget about gradient ascent and all. We are talking about a descent algorithm, right? A minimization, right? And therefore, right, what this means is that okay, then this quantity, right, is what then we need to appropriately pick, out of which this is already fixed, right? This is simply a gradient, and so which means that right, the whole control lies with what should be right a delta theta transpose. Okay, but the range of this quantity, right, but the range of delta theta transpose gradient L theta is such that suppose we said that the angle between them is let us say beta, right, such that cos beta is equal to again right delta theta transpose gradient L theta by norm delta theta norm gradient L theta, and this is a number that is greater than or equal to -1 and less than or equal to 1, right. So this quantity itself is such that if you take its ratio, right, with respect to its magnitude of the individual or norm of the individual vectors, okay, you get that, right, that's how it is. And therefore, right, therefore choose delta theta to be equal to minus gradient of L theta. Okay, if you do that, right, then what you find is at the right a numerator you will have norm of delta L theta squared, right. In the bottom, because of the fact that right, norm of delta theta, now delta theta is itself delta L theta, therefore you have bottom also norm square. The two will cancel off, and then right you will be left with -1, which is the smallest value, right, that the cos beta can take out there. So if you pick right any other angle delta theta, right, then this inequality, right, you won't be able to. I mean, you'll end up with a number where cos beta is actually right greater than -1. So a gradient descent is actually a principled way, right, in which right given any arbitrary surface, right, you can take as long as you are able to compute the gradient, which is why there was a differentiable sort of condition, right, that came right in between. Of course, there are other algorithms that don't even insist on that, but I think gradient descent, given that it is simple and easy to implement. So all that it requires is you should be able to have a differentiable function, right, and you see and always, right, remember when you are talking about L theta, if you are talking about a deep network, the L theta is coming at the end, right, that's at the output. Now this L theta, right, is going to be a function of so many things, right, in between. I mean, you've got your you've got the input layer, then you've got the hidden layer 1, hidden layer 2, and maybe you've got 50 hidden layers, and after that, right, you arrive at the output layer. Now when you express L theta in terms of all these weights and biases, right, you should not you should not end up with something which is actually a non sort of a differentiable entity, right, somewhere right along the way. Okay, so which is why that is something, right, that that we have to kind of say take care of.